Hello, guys. Nice to see you.
Hello. Hello.
How are you doing? Hi, hi.
Hello.
Hello.
Hi, nice to see you guys.
Hello. Good.
I'm doing okay, thank you. Hope you also. So, how things are going with your study? Are you already involved fully and everything works for you? Okay, that's important. Good. So, I guess other people will join if they want on the way. And if we don't have any questions to discuss right now, we can proceed further with our material discussion. Yes, you are right. We will go for laws of motion or Newton's laws today. So as you remember at the beginning, I specified that kinematics answers the main question where, like in terms of predicting where the body will be located in space after some time interval. And for that, it uses known like given information, which is initial position, speed, like velocity, and acceleration vectors. So the main goal for kinematics is to get this position vector. Like we're talking about some general cases, multi-dimensional space. We want to define the position vector as a function of time in order to be able to define position of the body at any moment of time. However, we don't ask any questions about the reasons for this motion, which we describe. And that is topic of dynamics. It's a section of mechanics, which deals with the reasons, means with forces. So force is a vector quantity, which has magnitude measured in newtons. And also it has direction. So that is very important because direction of force will also significantly define how this force acts on the body and what changes in the body's motion will happen because of the this force exerted on the body. So in order to start dealing with the understanding the reasons of motion and dealing with forces, we need to introduce three laws of motion or Newton's laws. And there should be several things specified before we start introducing and discussing them in details. First of all, these laws of motion, they were not derived based on some theoretical models. So these laws of motion, they were obtained based on observation. So these are empirical laws. And obviously we can observe specifically at that time when they were introduced, it's like early development of physics. Only relatively big objects which we can see and which move with reasonably small speeds, much smaller than speed of light. So if, for instance, we have a situation when speed of motion approaches like some fraction of speed of light, then this classical laws of motion, they are not working anymore because there is some relativistic mechanics which should be taken into account. If the size of the object go to some subatomic particles, then classical mechanics plays the role, and these laws of like quantum mechanics plays the role, and laws of classical mechanics doesn't apply anymore. So there are some limits of applicability for these laws of motion, which we're going to discuss, and that what you should be aware of. So we will start from the first and go step by step to the third one during our today's discussion. So let me change the screen. And let's define the first one. So we will talk about inertial frame of references a little bit later, just after introducing the first law of motion. We will give more explanation and some quantitative explanation, but as an introductory statement, inertial frame of reference is some frame of reference which doesn't move with any acceleration with respect to the body which we want to describe, like which motion we want to describe. So it should be either stationary with respect to this body, or it should move with some constant velocity, which doesn't change neither in magnitude nor in direction. So in the inertial frame of reference, a quasi-free or free body should not experience any acceleration. So this is pretty much the clear definition of the first law of motion. So what does it mean, quasi-free or free? Like free is when we have a body on which and there's no forces which are exerted on this body. So then we can consider this body as free. Quasi-free, which is more realistic case, when there are different forces exerted on this body, but they are acting on this body in that way that compensate each other, and the net, like resultant force, is equal to zero. So in general case, we can write for the first law of motion that the sum of all forces which act on the body is equal zero. So if this is true in inertial system of frame of reference, then velocity vector for this body should be equal either to zero or some constant value. So it should not change. So now So it actually gives us some relationship between net force acting on the body and change of velocity. No net force is equal to 0, no change in velocity vector. If the frame of reference with respect to which we consider this motion is inertia. So let us consider now two frames of reference. One is some inertial frame of reference, which we consider to be stationary, just doesn't move. So let's say X, Y. Then we have another frame of reference. X prime, Y prime. According to our conditions for this case, we assume that it moves with constant velocity vector with respect to stationary frame of reference Y and X. So we remember this. Now let us consider some point. Maybe let's put it a bit in different location. Will be more convenient here. Let's consider some point body A. First, with respect to this second mobile frame of reference. Here we will define its position as position vector r prime with respect to the origin of the second mobile frame of reference. Now we can also define the origin of the second frame of reference with respect to the first frame of reference. So this will be defined with the position vector r naught. And of course, we can define position of our body A with respect to the origin of the first stationary frame of reference. And that will be with vector r, position vector r. Okay, now we have all conditions. We have position vectors for all important points. And we already see from this figure that position vector r is equal to r naught plus r prime. So now let us take first derivative of this position vector with respect to time. So dr vector over dt is equal dr naught over dt plus dr prime vector over dt. So from previous discussions, we already know that first derivative of radius vector gives us velocity vector. So we can write here that v, the velocity vector of point A with respect to the origin of the first frame of reference will be equal to v naught vector, its velocity vector of the second frame of reference with respect to the first one, plus some v prime vector. So we assume that this body A is moving with some v prime velocity vector and some acceleration A prime vector. So now we see that if we go from second frame of reference where velocity is given by just v prime vector to first frame of reference, velocity is given by v which is different from v prime because we need to add this v naught vector. So let us do one more step and take first derivative of velocity vectors with respect to like over time. dv vector over dt is equal to dv naught vector over dt plus dv prime vector over dt. So again, from previous discussions, we know that this is like first derivative of velocity vector over time is by definition acceleration. So acceleration vector A of point A with respect to the first frame of reference is equal. So here we have dv naught over dt, and we remember that as the initial condition, we said that this is constant. So if we take derivative of a constant, we get 0. So this is 0. And then it will be equal to a prime vector. So you see, as opposite to velocity vector, acceleration vector doesn't change when we go from second frame of reference to the first frame of reference. That means that if we have some inertial frame of reference, we can always consider like many other inertial frames of references, which can be either stationary with respect to initial inertial frame of reference, or which can move with respect to the first inertial frame of reference with constant velocity vector in magnitude and orientation simultaneously, that means. So by definition, since acceleration is not a so-called invariant parameter, it doesn't change from going from one frame of reference to another, and velocity is actually a variant because we change velocity when we go between these frames of references. We can claim that this x prime and y prime frame of reference is also inertial frame of reference, within which, if we consider motion of some bodies, this laws of motion, like Newton's laws, they can be, this first law of motion can be applied. Okay, so with this, I think pretty much discussed. So we can proceed further and introduce the second law of motion. The second law of motion is given with quite simple equation. Usually in textbook, it's written like this. It's F is equal to m times A. However, makes more sense to introduce it as this form. A is equal to F divided by M. And that is because acceleration is the result of force acting on the body with some mass M. Obviously, it's important to highlight here that this force F, it's not just some force, like one of many forces which acts on the body. It is some net force. So F is equal to the sum of all forces which acts on the body, and then we get this F as a resultant or so-called net force acting on the body. So that will define how, with which acceleration this body will move. So technically, second law of motion gives us a very simple relationship between applied force from right side and acceleration from the left side. And there is some coefficient which is called mass, or to be more precise, inertial mass. And we need to discuss these parameters separately, like acceleration and mass, and define how we should measure it, because that will give us better understanding of its meaning and the physics behind this second law of motion. So let's start from the easy part and consider acceleration. Let's consider one-dimensional motion along a straight line. Tell me, please, any ideas how would you measure acceleration if there is such a task to do? It's pretty straightforward. I mean, we know that acceleration is change of, that's how fast, it describes how fast velocity changes over time. So for measuring acceleration, we obviously need to measure velocity at some initial point of time, then measure velocity at some other point of time, get difference of velocity, and divide it by time interval between these moments when we measured velocity. So that will give us the acceleration. So let's say if we have some uniform, like constant acceleration, that will be very straightforward. We just measure v2 minus v1 divided by time interval between these two measurements, which is also. Excuse me, do you have any question? Okay, looks like not. Please switch off your microphone, guys. Who is talking there, guys? Please switch off the microphone. Okay. Please keep your microphone switched off, because that interrupts the process. I believe it doesn't work. Can I see whose microphone is turned on? Okay. Now it's corrected. So let us continue. So it's in denominator here, we will have T2 minus T1. If acceleration is not constant, then we just need to try to measure these two speeds in as short time interval as possible. So we kind of put this delta t in approaching to zero. So in that case, if we can technically measure speed at very short, within very short time intervals, approaching to zero, we can approach also our measurement to instantaneous acceleration. So, but technically it's quite, it could be challenging, but it's quite clear how it should be done. By the way, do you know how devices which measure acceleration are called and what is the principle of their functioning, like most common, which are widely used, including in some mobile devices like smartphones, because you could check that most of smartphones nowadays, they have these accelerometers which show accelerations in 3 dimensions. So you can move your smartphone and it shows AX, AY, and Z accelerations in 3 dimensions. So this device is called accelerometer. And usually the most precise accelerometers, they work on the piezoelectric principle. So piezoelectric material, it's some crystal which can generate certain potential difference between its edges. Depends on if we compress it or stretch it. So if we have some piezoelectric crystal, then it's attached to some voltmeter. Then we have some metal ball, which is fixed with some spring. And under stationary conditions, it has some force F, which compresses this piezoelectric crystal, for instance. So it will produce some potential difference, which can be measured, and then it's set as 0 acceleration. Then depends if this system will move with some acceleration to the left or to the right, depends on direction. There will be some additional force because of acceleration. Is either will reduce this initial force or increase it. So this piezoelectric crystal will be either compressed or stretched. And that will change the potential difference at the edges of this piezoelectric crystal, which can be measured by some microcontroller and analyzed. If we calibrate this system, so we know this mass M, we calibrate this system, so we can find the relationship between potential difference between edges of this piezoelectric crystal and acceleration of this system. So that's the way how we can get it for one direction, let's say AX. And if we have 3 systems like this, which oriented perpendicularly to each other, we can get AX, AY, and AZ. Means we get all complete information about the acceleration vector of such accelerometer, such sensor, and can be used in different applications. So that is quite common approach to measure accelerations nowadays. Okay, so with acceleration, we figure out what now about the mass. How would you measure the mass?
Maybe by the weight.
You mean like scale? We can use some reference
Device.
Yeah. That is good approach, but let us talk a bit about different physical meaning of mass. We can consider mass as gravitational mass and as inertial mass. So what is the difference? Gravitational mass defines the weight of the body, and that is the product of mass and g, the acceleration of free fall. In other words, gravitational mass defines the interaction, like quantifies the interaction between the body and the gravitational field, because G is the strength of gravitational field. So imagine this. So we have interaction of the body with gravitational field. And then we have inertial mass, which technically quantifies how much body resists to change its velocity. Means to have some experience some acceleration upon action of some force. Some mechanical force is applied. Literally, you can have a body, you push this body, and mass, okay, inertial mass, will define how much it will resist to change its velocity. And there is quite a big fundamental difference between interaction with the gravitational field and interaction with your arm. When, like with your hand, when you push it. So we need to take this into account. It happens so that gravitational and inertial masses, they are equal to each other. However, from fundamental point of view, their physical meanings are quite different. So now, since we deal with second law of motion, we want to discuss how we can measure inertial mass. And that is different from using scales, because in scales, we technically measure weight of the body, not directly its mass, like inertial mass. We measure weight of how reference body with known mass interacts with gravitational field. Then we compare it to how our mass, some object with unknown mass interacts with gravitational field. And based on that, we can define the unknown gravitational mass. But here in the scope of the second law of motion, we want to deal with inertial mass. And in order to measure it correctly and then understand the meaning of this inertial mass, we need to design a little bit different experiment. So let's assume that we have some system spring, mass M1. It's some reference mass. We know this mass M1. This system is located somewhere in the outer space, and there is no other forces acting on this system. Then we apply some known force F to this body with the inertial mass M1. Definitely this will cause some displacement of this body. And then at some moment we let it come back to the initial equilibrium condition. So in this case, there will be some motion with acceleration A1. So force we can measure. We know how to get this force. And then we already discussed how we can measure acceleration. So we can measure this acceleration A1. Now we repeat another, so we repeat this experiment with another body with unknown mass M2. The same spring, there is another body M2. We apply the same force F. This body will displace from initial equilibrium condition, and that we stop acting with this force, let the system come back to the initial equilibrium condition. And there will be some acceleration, A2. So this acceleration will be different from the first case because M2 is different from M1. So from the second law of motion, we can write that A1 is equal to F divided by M1. So here I write like projections, not vectors. Then for A2 is equal to F divided by M2. We applied the same force F. So if we express this force from these two equations, we will get A1 times M1 is equal to A2 times M2. Now what do we have? We have known reference mass M1. We can measure A1. We can also measure A2. We don't know M2, so we can easily express it from this equation. M2 is equal to A1 times M1 divided by A2. This is the correct approach to determine, to measure the inertial mass of a body. So please remember this difference between gravitational and inertial mass and different approaches in measuring this mass. Because here, as you see, we highlighted that we don't have any other forces, and this means that there's no gravity. So we didn't involve gravity in these experiments. So it has nothing to do with interaction between these two bodies, which we consider in our experiment, with the gravitational field. Just inertial mass as a feature of resisting changing its velocity when there is some force, net force applied to this body. Okay, I think that this part we discussed also in details, and we can proceed further with the third law of motion, which is also very important. So if we have some force exerted on the body, there should be equal in magnitude but opposite in the direction, some reaction force. So that's why we can write, let's say we have some system. So this is third law of motion. We have some system of two bodies. So that's body one, body two. Then let's say body one exerts on body two some force F1, 2. Then there should be some force exerted from the side of body two on body one, which is equal in magnitude and opposite in direction, which is F21. So we can write that F12 is equal to minus F21. So this is the definition of the third law of motion. And this is very important in terms of defining the equilibrium, like stationary condition of bodies. For instance, we have such example. Let's say we have axis X, then we have some surface on which we mount a body with some mass m. Here will be the weight of this body, m times g, pointed downwards. And let's say we have also some force F applied to this body. So we have two forces acting in the same direction, force F and weight of the body. However, this body doesn't move anywhere. So according to the second law of motion, it should have moved with some acceleration, which should be A is equal to F plus mj divided by m. However, nothing happens, means that this is not true. And nothing happens because there is some reaction of this surface on the body. And this reaction, let's show it as capital N, will be equal, actually, let us take a look here on this, so we have this axis X, it's pointing upwards, so N will be positive, is equal to these two negative forces because they are pointing downwards. It will be weight mg and F. So it will be, so we can consider just projections of these forces on axis X. So it will be equal to minus m now let us consider vectors, and it will be in coherence with this definition of third law of motion. So here we have vector and minus F. So we have some net force with which the body is acting on the surface, its weight, and this additional force which we exert downwards, oriented downwards on the body. And this will be equal to the, in magnitude, to the reaction of the surface on the body, but different in, like opposite in orientation. So this is an example of this applicability of the third law of motion when we have some acting force and some reacting force. So let us summarize our today's discussion. So we introduced step by step 3 laws of motion. We highlighted initially that they have some limited applicability, which should be taken into account. First law of motion gives us the definition that in inertial system of reference, free or quasi-free body moves either with constant, so it moves along straight line without changing the orientation, with constant velocity, or just is stationary, doesn't move at all, velocity is equal to 0. We discussed what is inertial system of reference and how we can define it with respect also to another inertial system of reference. Then second law of motion, we introduced that acceleration is equal to force exerted to the body divided by inertial mass of the body. So also we discussed how exactly should be measured acceleration and inertial mass, highlighting the difference between inertial mass and gravitational mass. And gave some, like introduced the third law of motion when we have acting force and reacting force, which are equal by magnitude and opposite in direction. And highlighted on this experiment, like this example, what happens when we have some stationary body, when there is some weight, and this weight of the body is compensated by the reaction of the surface on which this body resides. That's why the body doesn't move while there are forces which are acting on this body. But if we add all these three vectors, n plus mg plus f, we will get 0. So this net force exerted on this body will be equal to 0, and that's why we don't have any acceleration of this body along axis x. Okay, if you have any questions, you are welcome, because this is pretty much everything what I wanted to discuss with you during this lecture. Next lecture on Friday, we will try to consider different examples of like application of laws of motion. Also like introduces friction forces, application of different laws of motion, and also we'll consider it in the example of some circular motion when we have also centripetal acceleration compensated by some other forces, like reacting forces. Okay, yeah, you raised hand. You are welcome to unmute yourself and ask questions. So you can interrupt me anytime you want in terms of asking questions.
Thank you for your attention. So there is a question. It's related mainly for the second law, when you explain the difference between inertial and gravitational masses. So when we measure gravitational masses, we are unable to obtain inertial mass because they should be computed differently. I mean, with using different methods. Or
okay, so this is a good question, because it's a bit confusing situation. The problem is that that is how it is. Gravitational mass and inertial mass, they equal quantitatively to each other. It's just the way we can measure mass with using scales, and that's what we always do, and we get some number which is applicable in terms of law of gravitational law, and also in terms of in the scope of the second law of motion, because quantitatively they are equal. But we wanted to highlight the physical difference between gravitational and inertial mass by designing some special experimental conditions of measuring it, because that, I believe, is a good way to show you guys how that these masses are different. And the fact that we design such experiment which doesn't involve gravity in determining the mass means that we exclude this option to measure gravitational mass, and instead we for sure measure inertial mass. And if we just use two masses, gravitational like scales, and this technique with a string and attached mass to it without neglecting with the effect of gravity, then we will end up with the same quantity. So it will be the same mass in terms of number, but different approaches experimental to measure it highlights the different physical nature of gravitational and inertial masses.
thank you.
You're welcome. Okay, guys. Thank you very much for your attention. Have a good day and take care. Hope to see you on Friday.
Thank you. Goodbye.
Thank you.
Bye-bye.
Goodbye.
Thank you.
Bye.
Goodbye.
Bye-bye.